Uh, yes, just a minute. Yeah. So n is a natural number. Yes, Cn of x is cyclic. Yeah, right. Yeah, yes. So start with which one? Uh, right. P square of x1 and so on. Okay, let's do that then. Start. So, so with P it is x naught and CP x1. Okay. Okay. Sorry. So maybe C of x0, whatever, 1. Yes. Then we have so on, maybe. Okay. So let's call this row 0, row 1, row 2, and so on. And then row n is CP xn to CP xn plus 1 by taking xn to p times xn. Right. Oh, yes, yeah, of course. Okay. And now we need to say what G is. Okay, so first let's prove that part only. So G is infinite. So, uh, yes, how do you prove that? G or I not. Yes, I mean it is, yeah, it is fine. So it's okay, but can you give a rigorous argument? Hmm. Yeah, okay. So how do you do that? Then right. So this kind of elements, yeah, maybe this kind of elements, pxk plus 1 and so on. Okay. Yes, and then it is okay, right? Yeah. I mean, it's a direct sum, so from there you can compare and say, right. Yeah. It's fine. Maybe so I'll skip this, but is it possible to say this from the universal property? Because so if you have this 1 minute, so how can you say this from there is the property for the direct limits? Yes, like that, yeah, that is so the something like this. So if you can find a group H, okay, and a map from this system to H such that xi and xj go to distinct things such that phi of xi is not equal to phi of xj, then we'll be done, right? Because there because this map phi will factor through this universal map through a map. Okay. This is like could be useful in more difficult versions of this kind of problems, right? Yeah. So can you just quick think of a group like that? Um, maybe so like some very simple map which forgets everything else but only remembers these two things. Yes, let's say that if xi is less than xj, then you could maybe simply you could uh, yes, so you could just take this to be c p to the j xj itself, assuming xi less than x less than, yeah, I mean sorry, I less than j, right? And then what should the maps be? The maps will just be these rows themselves and their compositions. Right, yeah. So it will be identity on the ith one and so on. And yeah, but no, but uh, so let's just check, see what these maps. because they have to also commute. So here the map could be just the composition. So these will be fine because this will just be like composition of row 0 till row j. This will be composition. I am just thinking what it should be for j plus 1. Maybe you say that. Yeah, there you have to be a little careful. Yeah, so there you can do quotient, I suppose, right? Yeah, because it's a higher order thing, so you can just quotient by this thing, and yes, something like that. But uh, let's just verify this. I don't want to end up making wrong conclusions. Just maybe here only we'll just verify this. So what we need to verify is is so you have this. Ah, oh, so you can scroll in this. Wow, it's a new thing. Okay, nice. So this is j plus 1, and so what do we need to do? So you had this map which is row j, right? I mean, you just need a map q so that the composition is identity on CPJ. Yeah, that is basically the commuting. It's this thing because there are two. You had two CPJs, and so yeah. So what should the map be? No, we had xj going to p times xj plus 1. Will that map exist? Yes. Yeah, let's that is also a problem with me. Let's just think about it for a minute. It will be clear. So yes, right. Yes. Yes. So there is a natural quotient map, right? It's a natural quotient map. Just send any element x to just its coset. Uh, Wait a minute. Yeah, let's see. So if, yeah, this map is okay, but yeah, will that work? So if you send one to P, right? Then you send P back to P. Yeah, so it does not work. Yes, yes, it doesn't work. Yeah, P and then you, yes, it certainly does not work. Ah, so you see there's a catch, right? So this does not work. So yeah, certainly this, no, this map cannot have a right inverse actually. Yeah. So no, so this choice of H actually doesn't make sense. Yeah. Yes. Yes. Because from other angle like this, that a group is in some sense these cyclic groups are in some sense indecomposable. You cannot write them as direct sum of two cyclic groups. And if this kind of map existed, any Q existed like that, then CPJ would become kind of a direct summand in some sense. So this doesn't work basically. Anyway, so fine. Yeah. This, yeah. Okay. Let's move on. I mean, the problem is done, but I thought we could. But yeah. Okay. Hmm. Okay. So let's look at the other part of the question then. Maybe we can hear it. Distortion. Yeah. So um, that is fine, I suppose. Yeah. Yes. So what is your reason? Uh, yes, it may not be a generator, but or will every element be a generator? Yes. Okay. So no, so my question is, will every element of G be the image of some generator, of a generator in one of the cyclic groups? Hmm. Yes, that is true. That is true. But also, I think this will also be true. This again probably not important, but every element should be a generator in one of them. Because if you look at its order, it's a power of prime, so it will be a generator from the first, like the earliest group from which it comes. It could be, so if you take any G in G, then if you look at the first group whose image is this G, then this would be a generator there. Yeah, somebody is, again, it's a trivial thing. It's just, yeah. So, anyways, what was the next thing? Yeah, but it is true. Hmm. Right. So let's record that. Every finitely generated subgroup is finite. Okay. And yeah, find all of them. Okay. Those, I think those will just be these cyclic groups, right? Hmm. Yes, yes. So yeah, it is clear, I think. It will be one of these cyclic groups. Yeah. So it's because like if you take a finitely generated subgroup, so generated by, let's say, H is generated by X1 up to okay, generated by Y1 up to YR, then we can assume that this all of this is inside some CPK XK. So it's a subgroup of this. Um, yes, it's a subgroup because so this direct limit map, I suppose, will be injective on on each group in this family, right? That's also, yeah. So then this subgroup of this and subgroup of this cyclic group is also always a cyclic group. So and it's a prime order, so it will be isomorphic to one of these. Yes, because H has some finitely many generators, and if this yi, let's say y1 is in xi1 and yr is in xir, right? Then these all these y1 up to yr we can assume is in cpir. We can push them. Yeah, composition of injective. Yeah. So then it's done, I think, through that. Yeah. But yeah, I mean, so it's not canonically one of these. So this H is not H is not one of these, like in natural sense, but it is isomorphic to one of these. Yes, right. It will be a subgroup. So this will be a subgroup of order p to the power r. So H is going to be uh, H is going to be some Cp to the power r. That's all we can say. But yes, it is not clear if H is the image of of Cp to R XR in this family. Yeah, that's the distinction. So I'll just write it here. So so we know that this H inside this G, let's say that H is CPR, or maybe uh, yeah, let's just say CPR. But then in this family also there is a CPR and so on. But it is not clear to me that this H is the image of this CPR. Yeah, I think it is. It is, right? Because so it's because if you take some CP to K XK, okay, such that from here you get H, some surjection. This we have, right? That's fine. This we have. But then basically H is the image of a subgroup of order p to the power r in this. But that is unique, right? Given any, right? So given a cyclic group of order n, and then you take a m divides n, then there is a unique, yeah, uh, yes, there is a unique one, right? And so if it's a unique one, but already you know the image of this one lands there as a subgroup of order P2, so it has to be that H, right? But then by the commutativity and so on, this should also have to land to H, right? Yeah, so it is in a canonical way one of these members. That's a nice thing. Yeah. Yes. So that's what I was trying in the beginning. If I could land that thing to that H, but it is it is not possible. That is not possible. That you get a map from the direct system to H, and it is fine. But that is how it is. I think. Yes. So what was the reason that for every M there is a unique cyclic subgroup of order M? Yeah, so we used this fact. Yeah, I think I see it, but just if you can say in some other way. So Cm, and then you have an n dividing m. Then there exists a unique copy of Cn, uh, right? And there is a unique H such that H is isomorphic to Cn, and H is inside this Cm. So why is it unique? So yeah, because the yes, 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 yes. That's what we used here. That's a fact, which you know. Yeah, so you take an element, take the generator. Yeah, I think it's fine. They will all appear in the same thing. Yeah, okay. Cool. That's okay. Okay, so basically we understand all the finitely generated subgroups of this. Yes. And they are all cyclic. So that's a thing to note that all finitely generated subgroups are cyclic, which means that they are generated by a single thing. Yeah. And then of course there are infinitely generated subgroups. I don't know. Are there any proper infinitely generated subgroups? Is that in? Oh, that's the next question. Okay, yeah. So yeah. So are there any infinitely generated proper subgroups? Oh, okay. Deduce that. Okay. So yes, you see that is also clear, right? Because if it is proper, then it should say it's a proper subgroup. Okay. Yeah, it has to miss. I mean, it would not it would miss some elements which are images of some p some cpk, right? Yes, yeah, okay, okay, let's try that. Every proper subgroup is, so let let g prime in g be proper. Yeah, so it is clear, I think. Yeah, because it is proper, so there is a g, so there is a g in G, which is not in G prime. So this G, let's say, comes from some CP, some CPN, capital N. and right, and we can take the smallest such n, right, n smallest, n chosen to be the smallest, then this G would be a generator of that, right? Yeah, because if it was torsion, then it would come from the previous one, right? So it implies that G is the generator. G is the basically G is that Xn. Yeah. So if you pick the smallest, then G, it implies by the smallest that G is equal to Xn. Yes, because if G is not the generator or is not a generator, yeah, so it's not Xn but is a generator. If G is not a generator, then the order of G is less than P to the n, and so G is of the form P times the generator or P square time. Yes, right. So in that way, and yes, so G is a generator. Yeah, you're right. It would not be that Xn necessarily. G is a generator, but then yeah, I mean you can pick that to be that Xn also because yes. Anyways, you can pick that, right? So yes, so that thing is, yeah, so it just means that the images of G prime is up till Cp minus Cp to the n minus 1, right? So it means that this G prime is contained in, meaning if it pull its inverse image, then it is contained in Cpn minus 1. Well, not the inverse image, I should say. What I mean by this is that the image of Cpn minus 1 itself contains G prime, right? Because every element of G prime is has order less than P to the n, right? So it's contained in this, and so it's finite. Yeah. Yes, the order thing we can use. Every element of G prime has order less than P to the n. Otherwise, that G would be in G prime, the small g. Yeah, then we are done. It has no properties. Yes. So is that the last part? Okay. Let's see. Yeah, then maybe they want to just know the group itself finally, if it's possible, or deduce that uh, can either of there's no proper infinite subgroup and no maximal proper subgroup. Maximal proper we have seen it has no maximal proper subgroup because it is cyclic group. Can either of these situations arise for subspaces of a vector space using dimension instead of order? Mm, okay, so let's see. So if you are saying V is a vector space that has no infinite dimensional subspace, right? Uh, yeah, proper subspace. So V has no uh, infinite dimensional, but that cannot happen, right? Yeah, if yeah, if it is still, then the G is finite dimensional. This implies G is finite, sorry, finite dimension. So yeah, it cannot happen. Simple. Identify a realization of G inside the unit circles. Yeah, so G is this G that we are looking at. This is certainly G is just the pth roots of unity, right? I mean, not pth, but some p power nth, yeah, roots of unity inside S1. Yeah, this should be the thing. But how do we prove this? Yes, because the order of every element is a power of p. So that means it should be like this. And yeah, yes. And you can also see that it is kind of like, I don't know, it is kind of like it is also Q mod Z. No, no. It is not Q mod Z. It is a subgroup of Q mod Z. So okay, I mean, all I'm saying is that this might actually be wrong. So let's see. So it's like if you take this kind of subgroup where you have AP to the K, where A is in Z, right? And K is a natural number, right? And you quotient this thing by Z. Then this I think this it's more clear that our G is this. Let's try to prove that. Yeah. Yes, this last one looks correct. And how do you prove it though? Yes, just map it in the natural way, right? Yeah. So what will that be? That should be like this. So you take like maybe C P K X K, and here you have elements like A X K, and just map it to A by P K. There's nothing else we can do really, like this. And let's see if it commutes. So if you take B X K minus 1, or maybe if this is P times like this, right? You see it's correct because this one we would map to by just the rule. I mean, if it is xk minus 1, then we will just map it to a by p power k minus 1. And then it commutes. But this maps to this. So this is correct, certainly. So really is this. And this sits inside this group Q mod Z. Wait, but what about the mod Z? And this is inside S1 because R mod Z is S1. But what about the mod Z, the kernel? Yeah, I mean, just map it in the other way and you see that Z is the kernel. So this is fine. So actually we have seen this, so we are able to see this inside S1. And now you just, these are just obvious things that I'm doing, nothing actually. Just P to the K and just map it to E to the I to pi A by P2. And that's the roots of unity, Pth roots. So now it is, yeah, yeah, okay. So we have actually we can identify the group. And this, I think, is called the Prufer group. If you have seen, maybe Prufer, you can read about this. I don't remember particularly anything, but I do know that these are very important groups. But I, I don't remember how. Actually, just let me see. So there was once recently. Actually, I was attending a seminar where they were trying to prove something. Yeah, so it was something where they were generalizing some things from finite from p groups to Prufer groups, because these are, as you just what we proved, these are direct limits of. Yeah. Yes. So the talk, so I was actually made notes of that talk. Yes, so yeah, so this talk was, yes. So as I said, that these are used to generalize. I mean, these are some things where you can generalize some facts about p groups to these groups, right? So if you know something about p groups, you might be able to prove it for these kind of groups also. Okay, but yeah, that doesn't answer the question. Sorry, I don't know any good application. That is the problem. So like if you look at mod Z, which is a collection of all abelian groups, then you, yeah, just a minute. So if you take X to be a category, so if you just take all the if you just take all abelian groups, let's say, and then you have the theory of abelian groups. So if you look at theory of all abelian groups, so modules over Z, this is just another name for abelian groups. Now, what is theory of abelian groups? So theory of abelian groups would be a collection of axioms which is which are like statements, or which you can make first order statements, means using their existence for all and quantifying over elements, not over sets. Then you get a theory, which means statements which are true. And then why is this called theory of this? Because then if you look at a model where this is true, in some sense, basically some results which are true for this thing. And I suppose there are more conditions, but I don't know. Yeah. Then this theory is decidable in that has a meaning. Uh, but let me first see if there is anything to say which I can actually. Yeah, I am not prepared. That's the problem. Don't know. Yeah. By the way, this has this. I believe that this is the symbol for this Prufer groups. I'm not correct. Mm, yeah, there are some things. That's all. I don't know very well. Yeah. Yes, yes. So since, yeah, exactly. That's the thing. So there is, I have noted down the name of the speaker so you can read about it. Sorry, I don't have the full name. So this is the name of the lady, and this topic would be model theory of modules. Yeah. Yeah, it might be some paper. Yeah. So if you look at this person's thing, then you might get this. Yeah. But I mean, but model theory for modules would also have books about it. So there is a book by marker. This is elementary. These papers I do not know. If you can read, you can read. I mean, I could try to read with you, but that I don't know them as such. So marker. This book is model theory. This book is easier to read. I have read parts of it at one point. Here also you would find applications of model theory. But how does model theory come in? It's not exactly clear. Uh, Basically, it's something like, I mean, if you want some like computationally nice class of a billion groups, then these are one of them, Prufer groups. Or rather, these are the only ones, the p-adic groups and Prufer groups and p groups is kind of, yeah. So basically these appear in the some sort of classifications, like all groups for which some nice property holds. And yeah. But yeah, I don't know anything more. Yes. So that's it. Would you like to tell me about the Hodge diamond thing today? If you like. Okay. Sure. Yeah, you can tell me that because I don't know what that is. So yeah. And yes. Yes. Okay. S- Yeah. These are the things. This is a group, and I don't know what you can do about this group. It is this a discrete group? Yes. I mean discrete in the sense that I mean discrete. I mean just as a subset of S1. I mean I'll be interested as subset of S1 because this way it's quite bad. If you look at it, Q mod Z, I mean, it is the same. Yeah, whatever. I mean, yeah. Yeah. Okay. Yeah. A subset of S1. So is it discrete? I mean, is the topology discrete? So meaning is around every point, right? Around every pth root of unity, is there a neighborhood where there are no other pth roots of unity for any p to the kth roots of unity for any k? Right? That is one of the things which you can think about. That I don't know. Should be easy. Yes, yes, exactly. I should write it. That's the thing. Yeah. So you look at G inside S1. So this we understand what we mean by this. Um, yeah. So is G discrete? So around every point, is every point an open set? This should be easy. Yes. Yeah. Yeah. Are these isolated points? Yes. That should not be difficult. Uh, oh, hmm, no, it cannot be discrete. Yeah. It can be discrete. Wait. It's a subgroup and it is certainly not cyclic, right? G is not cyclic. So G is dense. So you can prove that a subgroup of S1 is either cyclic or dense. Yes, yes. That's one of the nice things. Just like, yeah, you may have seen that in other places, this kind of statements. Like, yeah. Like you've seen, like if you take an irrational number and then let's say alpha, then you take n alpha, a fractional part of n alpha, then that's a dense subset of 0 comma 1, if you have seen that. And that's this statement is like that. But yeah, is it discrete? Yes. Yes. Yeah, so if it is, you see, I think answer should be no, because if it is, if it is discrete, then it is open. And now now we have open and dense. And yeah, so if it is open and dense, then it should be disconnected. Then S1 becomes disconnected, because then you're looking at S1, then you can look at the cosets of G, right? So some alpha G and so on. It's not countable, so but yeah, something like this, right? And these are disjoint and they are all open. But then that makes it disconnected, because you can just take the union of these and then yeah. And in general, you can understand, like if you have an open subgroup, that's bad, right? It doesn't. It actually, it is not. It's nothing about dense, right? If you just take open, sorry, if you just take open subgroup, proper subgroup, that will make the space disconnected. Yeah, that's the point. Because of these cosets, it doesn't even have to be a billion or anything. So open subgroups are, we don't like proper open. Yeah, and discrete means open because every point is open. So no, wait. Yeah, I mean, no. I was saying something wrong. No, wait. What am I saying? Yeah. No, I think we are saying something wrong. I mean, discrete doesn't mean it's open, of course. No, yeah. The point is open in G. It's not, it has to be open in S1. No, sorry, it doesn't. That's wrong. Yeah. A point is discrete, point is not open. That's wrong. Yes, so like discrete doesn't imply open, because a single point is also discrete, but it is not open. I mean, open in the bigger space. So discrete does not imply open. I used that this, I concluded that it is open, and then I made the remarks. Then I concluded it contradiction, right? So basically, it was completely wrong. So better to forget about it. I mean, this- uh, yeah, yeah. I mean, so I should say that discrete, yeah, under the subspace topology. Yeah, is it discrete as a subspace of S1 as a subspace of S1? That's all. I mean, it's a subspace, right? So is it discrete or not? That is the question. Yeah, it cannot be discrete because if you have a discrete sub, you cannot have a say if you have a discrete subspace of a compact set, it has to be finite. Otherwise, there'll be a limit point, right? I mean, a convergence of sequences is not discrete. No. Yeah, so that is a better reason. Yeah. So it's not discrete. It's not discrete, certainly. It is dense. It is not discrete. It's a dense subgroup. It's a nice dense subgroup if you see, because it just uses these p's. I mean, I would be interested if you could relate this to the p-adics. Somehow you see the p-adics seem to be dual to this, right? Thing. That should be of interest, I think. Like if I like, is there some way you can relate? So let's denote by this the group G. And then of course you have the p-adics, which uh, we should maybe denote like this if you like. And if you like, I mean, you can just the definition of this. So this is just the the one definition is, I mean, just if you maybe forgotten. So just that is if you take Z um, with the p-adic metric and take its completion. Okay, and p-adic metric was just that it's a norm which is just the so norm of an integer is just the p to the minus the order of prime in that. With this norm, you have a metric and then you complete it, right? Yeah. But you see the reason why I'm yes. And then you know that every so if you have x in this, then right, then this x has an expansion like this, right? You know this. Yeah. And we know that this is compact. It's a compact set, and this is but most interestingly, I suppose, is the most interestingly is the following thing that both are constructed by these sequence of groups, right? One by the direct limit and another by the inverse limit. Okay, so this is what we just saw today. Uh, question. This is multiplication by p every time, and then of course what we were doing is this earlier was this, which is the natural quotient. And the direct limit is this and the inverse limit is this. It's coming from the same family of objects. So there should be some connect. I don't know. There's no question even. So I, yeah, exactly. There is no question. That is the problem. I'm, yes, yeah. These, I mean, connection in the sense that like there should be some kind of a duality. I I feel, right? So okay. The question is this: that if you, that I should have asked, should say that if you take the dual, like the last day we were looking at that Pontryagin dual, right? Now we have a question, but this question, this is wrong. This is not, this is not the answer. I am sure it's wrong. But I can ask you, maybe because maybe you don't see it right now. I don't see it. I just know that it is not true from some theory. But it would be good to think about this. Yeah, yeah. Okay. Because there is something. There is something. You can, yeah, it is not true, and the reason is that if you take this map and you take the dual of this map, like if you take the dual of this group, you get this group again. Sorry, wait, wait. Yeah, right. You get this group, and you take the dual of this, you get this group. But if you take the dual of this map, I I am not sure if you get this map or the same map. Okay, there is something. Maybe first to think, then we can discuss this if you like next time. Yeah. Okay. This should be like related as part of a bigger picture. Like if you had a bigger language or bigger collection of objects, right, and some things relating them, then I think in that sort of relation, these two could be related by some duality kind of thing. Duality in the sense that you have some natural way to go from here to here, and then also to come back, right? Some, yeah, some construction that brings it back. That's why I was asking if it's discrete. So there's a fact that the dual of a compact group is always discrete. So that way you can say this is false. But it would be too good to see this explicitly. Yeah, what what actually fails. But anyways, yeah, you can think about it. Yes.